What you are about to hear is not speculation, not rumor, and not science fiction. 8 hours ago, on February 24th, 2026, NASA's Deep Space Network received a data packet from the James Webb Space Telescope with only a 0.004% chance of being a natural error. That number alone should make you pause, because what Webb detected coming from the tail of 3I, Atlas, should not exist. Imagine staring at a comet drifting through the vacuum of space. You expect ice. You expect frozen water, carbon dioxide, ammonia, and dust, the basic leftovers from the birth of a solar system. Comets are often described as dirty snowballs, fragile time capsules from the earliest days of planetary formation. At 14 UTC, today, that is exactly what astronomers expected to see. Instead, Webb's near-infrared spectrograph recorded a powerful, coherent plume of magnesium-iron silicate. In simple terms, it detected olivine, not just traces, not scattered grains mixed with ice, pure crystalline olivine, the same green mineral found deep inside Earth's upper mantle, a gemstone forged under immense pressure, shimmering in the solar wind, trailing behind an object that was supposed to be frozen debris from the dawn of time. This changes everything. Olivine does not form in cold space. It is born in fire and crushed by gravity. To create crystals of the size and purity 3I, Atlas is releasing right now, you need temperatures above 1,200 degrees Celsius and pressures equal to 40,000 times Earth's atmosphere at sea level. You need the interior of a planet, yet here we are, observing an object 230 million kilometers away, behaving like a fractured world, exposing its interior. When the Atacama Large Millimeter Array in Chile confirmed Webb's readings, scientists stopped assuming instrument error. The implications became precise and deeply unsettling. Comets do not have mantles. They do not have molten cores. They do not generate the pressure needed to forge gemstones. So astrophysicists are now asking a direct question. If 3I Atlas is shedding material from a rocky mantle, where is the rest of the planet? Even more troubling, the crystallization pattern matches Earth's geology to within 99.8%. This is not a minor anomaly. It challenges the standard model of comet formation. NASA's Jet Propulsion Laboratory immediately redirected deep space tracking resources because the ejection rate is increasing. At first, it was a trace signal. Now the plume is thickening, and the spectral intensity is rising. Pause for a moment and think about what that means. We are not simply observing a rock in space. We are examining what looks like the exposed interior of a destroyed world. When 3I Atlas was first cataloged by the Atlas Survey in Hawaii, its trajectory suggested a normal long-period comet, possibly from the distant Oort cloud, or perhaps an interstellar visitor like Oumuamua. Expectations were clear: water, ice, primitive organics, dust from an ancient system, nothing more. But on January 14th, 2026, the narrative shifted. That was the day the James Webb Space Telescope aimed its mirror at the object's developing tail. The mission was straightforward: measure water sublimation rates. Instead, Webb detected a sharp, high-intensity spectral peak at exactly 10 microns. In spectroscopy, a 10-micron spike is a fingerprint. It signals silicates, and not just any silicates. The lattice structure precisely matched magnesium-iron silicate. Geologists call it olivine. At first, researchers at NASA's Goddard Space Flight Center assumed calibration error. Space contains dust, yes, but olivine is dense and heavy. Finding it in a comet tail is like opening a snowball and discovering a polished emerald at its center. So they asked for confirmation. and confirmation arrived. Confirmation did not come from one source. It came from 3 independent systems using 3 completely different methods, and all of them reached the same conclusion. First, the James Webb Space Telescope identified the chemical signature of magnesium iron silicate in the infrared spectrum. Second, the European Space Agency's Gaia spacecraft detected something unexpected in the object's motion, a non-gravitational deceleration consistent with the loss of heavy material. The math showed that 3I, Atlas was shedding mass nearly 3 times denser than water ice. Third, the Atacama Large Millimeter Array, using its 66 antennas in Chile's high desert, measured the size of the particles in the tail. These were not microscopic dust grains. They were millimeter-scale crystals, visible, structured fragments. 3 instruments, 3 techniques, 1 identical outcome. The numbers were clear. 3I, Atlas, was ejecting green crystalline material into space. But that was only the first anomaly, the existence of olivine at all. On February 10th, the second anomaly emerged. Spectral analysis over 48 hours revealed that the concentration of olivine in the tail had risen to nearly 40%. Think carefully about that level of purity. Comets are chaotic mixtures. They contain ice, carbon compounds, silicates, metals, everything blended together. They are not refined bodies. To reach 40% purity in a specific mantle mineral requires a geological process known as differentiation. Differentiation happens inside planets. When a young world melts, heavy elements sink toward the core while lighter materials rise. Over millions of years, layers form iron at the center, silicate mantle above it, crust at the surface. This process demands sustained heat, gravity, and internal pressure. It does not occur inside small icy comets, yet 3I, Atlas, appears to contain differentiated material. As the object approaches the Sun, its surface ice sublimates. The frozen outer layer evaporates, weakening whatever structure holds the interior together. With the ice acting as glue, once it melts, the heavier crystals inside begin to fall away. Models predict that within 72 hours, solar radiation pressure could produce a visible curtain of reflective crystalline particles, a phenomenon never observed before in modern astronomy. But here is where the mystery deepens. If 3I, Atlas, is shedding mantle material, which planet did it belong to? When scientists analyzed the isotopic ratios of oxygen locked within those crystals, they expected variation. Mars has a specific ratio. Asteroids in the main belt have another. Kuiper belt comets carry distinct isotopic signatures. Instead, the results returned something unsettlingly familiar. Before addressing that conclusion, the physics must be considered. Even if we accept that this is planetary material, the object's trajectory raises another problem. A body this dense should not be traveling at its observed velocity. 6 hours ago, updated tracking data from the European Space Agency indicated that 3I, Atlas, is not simply falling toward the Sun under gravity. It is being pushed. To understand the scale of this contradiction, consider the pressure paradox. Space is almost empty. Pressure approaches zero. Temperatures hover near absolute zero. Under those conditions, silicon and magnesium form loose dust grains. They do not crystallize into dense, structured minerals like forsterite, a specific variety of olivine that requires at least 40,000 atmospheres of pressure and temperatures exceeding 1,200 degrees Celsius. Comets form in the cold outskirts of solar systems. They are gentle accumulations of debris. They do not possess molten interiors or tectonic systems. They do not generate crushing internal gravity. Yet 3I, Atlas, is releasing millions of tons of high-pressure crystalline material. NASA's internal models present only two possibilities. Either 3I, Atlas is not a comet at all, but a fragment of a destroyed planet, a shard of mantle torn from a once-formed world, or our understanding of solar system formation is incomplete. And then, on February 18th at 4:30 UTC, the situation escalated. Gaia detected a sudden shift in trajectory. Normally, comet outgassing produces a mild thrust. This was not mild. The acceleration vector aligned precisely with the direction of crystal ejection. The object was not drifting. It was actively accelerating in correlation with mineral release. That was not predicted. And it forces a new question. That acceleration forced researchers to quantify what they were seeing. The probability of a standard comet containing a dense, iron-rich mantle fragment is less than 0.001%. The probability of that same object accelerating in a direction precisely aligned with the ejection of heavy crystalline material is statistically negligible. For both events to occur in the same body during the same observational window pushes the odds toward 1 in several billion. In over 4 million years of modeled cometary behavior, nothing like this combination has been recorded. When the Jet Propulsion Laboratory labels a trajectory anomalous, it is not a casual remark. Orbital paths are updated constantly, but 3I Atlas had its parameters revised 3 times in 24 hours by the International Astronomical Union. That is not routine maintenance. That is emergency recalibration. The data indicates the olivine crystals are not simply drifting away under sublimation pressure, they are being expelled with measurable force. Imagine a pressurized container in vacuum that suddenly fractures. Material does not float out gently, it bursts outward. That is the pattern being observed. And yet, despite the volume of mass loss, 3I Atlas remains structurally intact. If you compare the estimated mass of expelled olivine against the object's calculated total mass, something does not add up. By all models, the object should be destabilizing. It should be fragmenting. Instead, it holds together, implying that beneath the evaporating ice lies an extremely dense core, denser than known cometary nuclei, denser even than most asteroids. The most plausible explanation for such density is a core composed of iron-nickel alloy. That composition, paired with a silicate mantle, defines a planetary embryo, a body that once underwent internal differentiation, not a dirty snowball, but the early framework of a planet. This realization prompted the Minor Planet Center to issue an emergency classification upgrade. But the most disturbing evidence was still pending the isotopic analysis. On February 20th, at 7:15 UTC, the Keck Observatory in Hawaii directed its high-resolution spectrometer toward the tail of 3I Atlas. This time, scientists were not searching for mineral types. They were measuring isotopes, specifically oxygen 16, oxygen 17, and oxygen 18. These isotopes act like planetary fingerprints. Each planetary body forms with a slightly distinct ratio shaped by the conditions of its birth. Mars has one ratio, the Moon has another. Asteroid Vesta carries its own signature. Objects from the outer solar system display different isotopic balances due to colder formation environments. When the data returned from Keck, researchers compared it against every major catalog in the database. It did not match Mars, it did not match Vesta, it did not align with Kuiper belt comets or Oort cloud bodies. It matched Earth. The oxygen isotope ratio embedded in those green crystals is identical to terrestrial rock within a probability margin of less than 1 in 10 billion. That figure is not symbolic. It is a statistical calculation based on known solar system distributions. The implication is direct and unavoidable. Either 3I, Atlas, is composed of material originating from Earth, or it comes from a body that formed under nearly identical conditions in the same region of the early solar nebula. Two primary scenarios now dominate scientific discussion. Scenario 1, 3I, Atlas is a fragment of early Earth itself. Around 4.5 billion years ago, a Mars-sized protoplanet named Theia collided with our young planet in a catastrophic impact that eventually formed the Moon. During that collision, enormous quantities of mantle material were ejected into space. Most debris coalesced into the Moon. Some fell back to Earth. A fraction may have escaped entirely. If 3I, Atlas, is one of those escaped fragments, then it is a lost piece of our planet, returning after billions of years in deep space, a remnant of Earth's infancy. Scenario 2. It is a surviving fragment of Theia itself, the planetary body that struck Earth and was largely destroyed. If so, this object carries the preserved mantle chemistry of a world that no longer exists. Either explanation reshapes planetary science, but the story does not end with isotopes. Because as 3I, Atlas approaches perihelion, its closest point to the Sun, the rate of sublimation is increasing, and so is the exposure of its interior. And what may be revealed next could extend beyond mantle minerals. It could redefine the origin of life itself. As 3I, Atlas moves closer to the Sun, surface temperatures are rising rapidly. The outer shell of ice, which has concealed the interior for billions of years, is evaporating at an accelerating rate. With each hour, more of the crystalline core becomes exposed. NASA has already allocated emergency observation time on the James Webb Space Telescope for the next 72 hours. This is not routine monitoring. It is targeted investigation. Scientists want to know whether olivine is the only mantle mineral present, because if differentiation occurred within this body, there could be additional compounds embedded deeper inside minerals that only form in the presence of liquid water or sustained geothermal activity. Let us separate confirmed facts from speculation. 3I, Atlas is ejecting pure crystalline olivine. The mineral requires extreme pressure and heat to form. The object's density implies a differentiated internal structure. Its oxygen isotope ratio matches Earth within 1 in 10 billion probability. Its trajectory includes acceleration aligned with mineral ejection. These are direct observational results from Webb, Gaia, ALMA, Keck, and multiple tracking systems. This is not theoretical modeling, it is measured data. Now, consider the implications. If 3I, Atlas, is a fragment of primordial Earth, it carries material from a time before stable oceans, before continents, before life. It may contain trapped volatile compounds, early carbon chemistry, perhaps even isotopic records of the prebiotic environment. It would represent the oldest preserved terrestrial matter ever studied. If it is a fragment of Theia, then it offers something even more rare, direct physical evidence of a lost protoplanet. For decades, Theia has existed primarily as a theoretical construct supported by lunar formation models. A surviving piece would allow direct chemical comparison between Earth and the impactor that reshaped it. There is also a third possibility, less comfortable but scientifically necessary to consider. 3I, Atlas, could be a rogue planetary fragment from another star system that formed under nearly identical isotopic conditions. While statistically unlikely, it cannot be ruled out without further data. If true, that would imply a level of chemical uniformity across stellar nurseries far beyond current assumptions. At this moment, the object is nearing perihelion. Solar radiation pressure is intensifying. The sublimation rate has doubled in the past 24 hours. The James Webb Space Telescope is locked onto the nucleus. Detectors are calibrated for continuous spectral capture. Every new photon is being recorded. Within the next 12 hours, models predict that the final layers of surface ice will thin dramatically. For the first time in human history, we may observe the exposed interior of what appears to be a planetary mantle fragment in real time. The veil is lifting. The data stream is active. The tracking arrays are synchronized. The orbital parameters continue to update as new measurements refine velocity vectors. What remains uncertain is not whether 3I Atlas is unusual, that is established, but what else lies within it. Because if olivine exists in such concentration, then other high-temperature minerals may follow. And if water-altered silicates appear, the conversation expands from planetary destruction to planetary habitability. The clock is no longer measured in decades or even years. It is measured in hours. And as instruments focus on this object racing toward its closest encounter with the Sun, one question remains unavoidable. Whatever 3I Atlas truly is, a fragment of Earth, a remnant of Theia, or something entirely unexpected, what will it reveal when the last of its ancient ice finally disappears? As 3I Atlas closes in on perihelion, the transformation becomes impossible to ignore. The outer ice shell, which has protected the object for billions of years, is now vaporizing at a rate that exceeds earlier projections. With each rotation, more of the interior is exposed to direct solar radiation. The James Webb Space Telescope continues uninterrupted spectral analysis, and what it is seeing confirms that the olivine signature is not fading. It is intensifying. The concentration of crystalline magnesium iron silicate is now consistent across deeper layers of the ejecta plume. This tells us something critical. The mineral is not embedded randomly in pockets of ice. It is structural. It is foundational. The body appears to be built around it. At the same time, updated mass loss calculations show that the object is ejecting material at a rate that should destabilize a typical comet nucleus. Yet 3I Atlas remains intact. Its rotation period has shifted slightly, but there is no sign of fragmentation. That stability strengthens the hypothesis of a dense metallic core anchoring the structure from within. An iron-nickel center surrounded by a silicate mantle is the textbook blueprint of a differentiated planetary body. Then came the next layer of analysis. Researchers began scanning for hydrated mineral silicates that form only in the presence of liquid water interacting with rock. If detected, such compounds would suggest that this object once experienced not just heat and pressure, but also water-rock chemistry. Preliminary signals hint at subtle absorption features near wavelengths associated with hydroxyl groups. The data is still being processed, but even a trace detection would expand the implications dramatically, because now the question would not only be whether 3I Atlas was once part of a planet, the question would become whether that planet ever hosted environments chemically similar to early Earth. Meanwhile, the trajectory data continues to complicate the story. The acceleration aligned with mineral ejection has not diminished. In fact, as solar heating increases, the force of expulsion has grown more precise. The vector remains consistent with internal pressure release rather than surface sublimation alone. That suggests trapped volatile gases beneath the mantle layer, possibly sealed for billions of years under frozen pressure, now venting through fractures as the outer shell weakens. The probability models have been recalculated again. the combined likelihood of a standard comet containing differentiated mantle material, matching Earth's isotopic signature, and exhibiting sustained directional acceleration is effectively beyond conventional expectation. The scientific language is careful, but the meaning is clear. 3I, Atlas does not behave like any comet in recorded history. As this realization spreads through the astronomical community, debate narrows around two dominant origins. If this object is a fragment of primordial Earth blasted into space during the collision with Theia, then it represents the oldest returning terrestrial material ever observed. It would be a preserved sample of Earth's mantle from before oceans stabilized and before life began to shape the atmosphere. If instead it is a surviving piece of Theia itself, then we are witnessing the physical remains of the protoplanet whose destruction gave birth to the moon. That would provide direct chemical evidence of an event that reshaped our world 4.5 billion years ago. There is no comfortable middle ground. The isotopic match demands explanation. And as 3I, Atlas reaches its closest approach to the Sun, the final veil of ice is thinning. Within hours, the most concealed regions of the core may be directly observable. The instruments are calibrated. The data stream is continuous. What emerges next will not just refine this discovery, it will define it. Perihelion has arrived, and with it, the moment scientists have been anticipating since the first anomalous signal appeared. Solar radiation now strikes 3I, Atlas, at maximum intensity. Surface temperatures have surged, and the sublimation front has migrated deeper into the body. What was once a frozen exterior has become a thinning membrane, exposing the interior architecture to direct observation. The latest spectra confirm that the olivine-rich layer extends far beneath the surface. The uniformity of the mineral distribution reinforces the conclusion that this is mantle material, not contamination or external coating. Density estimates derived from orbital perturbations continue to support the presence of a compact metallic core. Every independent measurement converges toward the same structural model: iron, nickel center, silicate mantle, volatile outer layer. The isotopic evidence remains unchanged. Oxygen 1:6, oxygen 1:7, and oxygen 1:8 ratios align with terrestrial standards to an extraordinary degree of precision. Follow-up calibration checks have eliminated instrumental bias. Cross-referencing with lunar samples, Martian meteorites, and asteroid fragments confirms the uniqueness of the match. Statistically, the odds remain less than 1 in 10 billion that this alignment occurred by chance. If 3I, Atlas, originated from Earth during the Theia impact, then it is a relic of planetary violence that preserved a snapshot of our earliest geological state. It would mean that fragments of Earth escaped complete reintegration and survived in distant orbits for billions of years before returning inward. If it originated from Theia, then it represents the first direct physical evidence of a lost world, long theorized but never sampled. In that case, this object carries the chemical memory of the body that collided with Earth and altered its destiny forever. A third possibility, though less favored, remains scientifically open: formation within a neighboring stellar nursery under nearly identical isotopic conditions. If that were true, it would imply that planetary formation chemistry is more uniform across star systems than current models suggest. Even that outcome would demand revision of foundational assumptions about solar system diversity. As observation time continues, researchers are preparing for the next phase. High-resolution thermal mapping will attempt to detect internal heat gradients. Polarimetric studies may reveal surface texture variations consistent with exposed mantle rock. Plans are already being drafted for for potential future interception missions should orbital mechanics allow. For now, what we know is solid. 3I. Atlas is not behaving like a conventional comet. It is shedding planetary mantle material. It possesses a density profile inconsistent with icy aggregates. It is accelerating in a manner correlated with internal mass ejection, and it carries an isotopic signature that mirrors Earth with staggering precision. This is no longer a question of anomaly, it is a question of origin. We are witnessing either the return of a fragment of our own planet, the preserved remains of Theia, or a planetary shard from a system that mirrors ours more closely than imagined. Whatever the final classification becomes, the implications will echo through planetary science for decades. The telescopes are still watching, the data is still arriving, and the story is still unfolding in real time. If you want to stay ahead of every update, every discovery, and every breakthrough connected to 3I, Atlas, and the future of planetary science, make sure you subscribe, turn on notifications, and join us as we continue to follow this extraordinary object to its final reveal.